Hello, this is Miss Moore, and today during chemistry, we're going to discuss single replacement reactions with metals. Today's essential question: how are the products of single replacement reactions determined? So single replacement reactions are also known as single displacement reactions. And during these types of reactions, atoms of a single element replace atoms of a second element in a compound. That sounds a little confusing, maybe not the best sentence, but let me show you the general reaction. Hopefully that helps. So what we're saying here is that our A is some sort of single type of atom. Okay, and AB is an ionic compound. And hopefully what you can see happening here is that when you go from the reactant to the product side, what happens is that the single atom A swaps places with the X in the ionic compound. That's a single replacement reaction. So a single atom replaces or displaces an ion in an ionic compound. So that being said, it's important to note that single replacement reactions occur with ionic compounds, meaning that our AB over here needs to be ionic. All right, let's move onward with our discussion of single replacement reactions. So during a single replacement reaction, for now, two different things can occur. First, a metal can replace a metal in the compound, or a positive replaces a positive. So meaning, if you have the metal as your single type of atom, then it'll replace the metal in your ionic compound. Conversely, if you have a nonmetal as your single type of atom, so for both of these, that's, okay, I'm going to scroll up for just a second. When I talk about the single atom, I'm talking about the A in our general equation. Okay, so this would be our A or our A. So if our single type of atom is a nonmetal, then it's going to replace the nonmetal or the negative in our ionic compound. All right, so now really quick review on metals and nonmetals. I'm guessing you know this, but just in case. So our metals are all these guys to the left of the jaggedy line. So these are our metals. And the ones to the right of the jaggedy line, those are our nonmetals. Okay, just quick review on that. All right, so let's try this. Let's go through the steps to write or complete a single replacement reaction. And we will do this, we'll go through the steps at the same time we'll go through the example of calcium plus hydrogen fluoride. All right, so here we go. First of all, determine which atoms are cations, which, remember, cations are the metals, and which are the anions, which are going to be our nonmetals. And while we're doing that, we may as well get the charge because we're going to need those later anyway. So starting with calcium, scroll up to my periodic table here. Calcium is right here. He's a metal, right? He's going to lose 2 electrons, making him isoelectric with argon. So he's going to go from 20 to 19 to 18. So he's going to lose 2 electrons, giving him a 2+ charge. All right, so that's a metal cation. Would be a cation. All right, next is hydrogen. Hydrogen's a little funky. He always has been. So there's hydrogen. He's hanging out with the metals. So he's going to act like the metals, which means he's going to lose an electron. And he only has 1, so he's going to lose 1 electron, being isoelectric with no 1. So if he loses 1 electron, he is going to have a 1+ charge. All right, and then we have fluorine. Fluorine is right here. He's going to gain, he's a nonmetal, so he's going to gain an electron. He's going to go from 9 to 10 electrons, making him isoelectric with neon. And if he gains an electron, he has a 1- charge. Okay, so hopefully so far so good. This was review. All right, so that was step 1. Step 2, determine which atom is to be replaced. So remember what we just talked about is that if you have a metal as a single atom, it's going to replace the metal in the ionic compound. So that means we're going to have H and Ca swapping places, or the Ca is going to replace the H. Okay. All right, so we already went through this, but I guess it's good to drop it down again. A positive or a metal will replace a positive or a metal. Yeah, that's like said twice. A positive will replace a positive will replace a positive, or a metal will replace a metal. Okay, so which is the situation we have. All right, write the skeleton equation. So we started out with, what did we have to begin with? We had Ca plus H, keeping with the same color scheme, HF. And remember, we decided that Ca is going to replace H. So I'm going to write the H by himself plus CaF. Okay, that's just a skeleton equation. We just made, we just wrote the compounds down, but we haven't done anything else. So if you're seeing some mistakes there, it's all right. That's good. All right, so next step is to make sure that all ionic compounds are neutral. So if you remember up above, let's scroll back up there. Our Ca was a 2+, our H was a 1+, and our F was a 1-. So Ca is 2+. Don't know what that's about. Try that again. 2+, and our F is a 1-. So that is definitely not a happy couple, right? We need 1 more fluorine so that we have equal amounts of positives and negatives, right? So we have 1 Ca and 2 Fs. So our formula is going to be CaF2. Get rid of that stuff. All right. CaF2. Now, the next thing you have to look at is diatomics. So anytime we write a single atom, we've got to check to see if we have a diatomic. And remember, Hofbrinkel or HN7, our diatomics are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So those are our diatomics. And we do have a diatomic, right? Hydrogen is one of our diatomics, which means he needs to be H2. All right. Last step is to, make sure all our ionic compounds are neutral. We did that. Check for diatomics. We did that. Now we need to balance the equation. All right, so let me rewrite this equation so I have a little bit of room to work. We have Ca plus HF produces H2 plus CaF2. All right, so CaHF, we have 1, 1, 1, 2, 1, 2. All right, so to make these neutral, what do we need to do? Our CA's look good, H is not too much, so we'll put a 2 in front of HF, giving us 2 H's and 2 F's, and I think we fixed it. All right, so that's really what you do for single replacement reactions with a metal. Now, before I say goodbye, let's try one more problem. So single replacement reaction practice, we've got magnesium and sodium chloride. So step 1, figure out the cations and the anions, the metals and the nonmetals, and write down their charges. So we've got magnesium, which is a metal, going to lose 2 electrons, right? He's going to go from 12 to 11 to 10, being isoelectric with neon. If he loses 2 electrons, that means he has a 2+ charge. Sodium, also a metal. He's going to lose 1 electron to become isoelectric with neon, giving him a 1+ charge. And our last is chlorine, non-metal. He's going to gain 1 electron, becoming isoelectric with argon, giving him a 1- charge. All right, next step is write the skeleton equation. Or no, next step is figure out who's going to swap places. Well, we have a single metal atom, which means he's going to swap places with the metal ion. So on the product side, we're going to end up with Na by himself, and Mg is now going to hook up with Cl. And let's get those charges in there. All right. So now that we have our skeleton equation, the next thing we need to do is check for diatomics and make sure ionic compound's neutral. Sodium, is he one of our diatomics? Is he a hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, or iodine? He is not, so Na is fine like he is. Magnesium chloride, not neutral, right? We need another negative charge here. So now we have 2 positives and 2 negatives. So that makes our formula MgCl2. All right, and let's get rid of all this extra stuff now. Make it a little easier to work with. We don't need this anymore. All right, and the last step is to balance. So we have magnesium, sodium, and chlorine, 1, 1, 1. Let's see, 1, 1, 2. All righty. So magnesiums and sodiums look good. Chlorine, not so much. We need another chlorine on the reactant side. So we'll put a 2 in front of NaCl, giving us 2 sodiums and 2 chlorines. So while fixing the chlorines, we messed up the sodiums. But if we put a 2 here, now we're good. All right, one last thing before we finish this up. During the lecture, I implied that the single metal atom always replaces the metal cation in the compound. That actually isn't true. So later, in a later lecture, I will teach you how to determine or predict whether or not this metal atom will indeed replace the metal cation, the metal cation in the compound. Okay, so that is it for today. Have a good one.